The next problem-solving tip we're going to look at is called visualize the problem. This is one of my favorites because I tend to think in pictures and I see things better when they're sketched out. So this is the description that we use from your book. It says, organize the important information and your thinking. Draw a picture, make a table, or sketch a graph. These can help you see the relationship between two quantities, estimate a solution, and or give your ideas for writing the equation. Table is a handy way to keep track of your guesses too. Now I'll tell you that the way I'm going to explain this is not so much about graphs and tables, although remember back to the example of changing a motorcycle tire. I've now seen people change motorcycle tires in vastly different ways using different tools and very different techniques. And so I'm not going to say don't use graphs or tables. I'm going to explain to you the way it works best for me. And the key for you is to practice all these different things. Try lots of different things. Try to find ways that work for you to solve word problems. Because you can't just keep going on saying, well, I have a really hard time with word problems. I'm not good at word problems. What we want you to do is, we understand that you have trouble with that, but we want you to work on that. Try different ideas. Look at the way other people solve it. Try to figure out some things that'll work for you. Okay, so we're going to try visualize the problem. And if you like to think visually, you find yourself doodling when I'm boring you, or you like to draw, this might be a good tip for you. So again, I like to do the sketch or the drawing part, but the other parts of this problem-solving technique are fine too. So here's a problem that from your book. Don't solve the problem, use visualize the problem to try to find the equation. It says Bill is installing a drip system to water his yard more efficiently. The irrigation tubing he purchased comes in rolls of 50 feet. He'll cut the roll into 4 pieces. The second piece will be 5 feet longer than the first. The third will be 10 feet longer than the first. And the fourth piece will be twice as long as the first piece. How long is each of the pieces he'll cut? Now I know this is the sort of problem that gives math teachers and algebra a bad reputation, but before you make too much fun of us when you see a problem like this, remember that what we're trying to do is there really are application problems for algebra in all sorts of fields, and you really do wind up having to build equations out of word problems or just real world situations. And so we're really just playing with things like this. We don't really think anybody ever installs a drip system by cutting a piece that's 5 feet longer and 10 feet longer and twice as long. And we don't think people do problems like this that way, but we're using it to help you learn these techniques so that when you get to situations where you might use it, you'll have practiced it. So we always, when we look at a word problem, we want to figure out what we're looking for. And what we're looking for is how long is each of the pieces he'll cut. So if you're going to visualize this, the reason I think this is a good one for visualize the problem is we're talking about a tangible object, this irrigation tubing that comes in rolls of 50 feet, and he's cutting it up. And so that makes it easy for me to visualize. So first we draw out 50 feet of tubing. Remember, we're not interested in drawing this to scale or anything. We don't care if it's sloppy or neatly drawn. That's not the point. So then we think of that tubing. We go back and reread the problem, and we think about how we're cutting it up. And so we're calling piece 1 X because that's how the problem defined everything. It said we cut it into 4 pieces, and then it says the second piece will be 5 feet longer than the first. So that's why we're calling the first one X, because that's what all the other ones are defined according to in the problem. Third one is 10 feet longer than the first one, and the fourth piece will be twice as long as the first piece. But really the very first thing you're doing is not even putting those on there. You're just picturing cutting it up into 4 pieces. So that's reminding yourself that it is 4 pieces. And then, again, it doesn't matter if it's to scale. If you're, this piece down here is the one that's going to be twice as long. If it doesn't really look twice as long, doesn't matter. So don't get too caught up in the drawing. But so once we cut them up, then we go back to the word problem and say, all right, I'm going to call the first one X. And then the next thing says the second piece will be 5 feet longer than the first. So 5 feet longer becomes this one. And then it says the third one will be 10 feet longer than the first. So that becomes that one, the first one plus 10 feet. And then the fourth piece will be twice as long as the first piece. So that's 2x. So we're not trying to get all the way to the end yet. We're just doing a little at a time. We drew our piece of tubing, we chopped it up into pieces. You could even decide to not even draw the 5 different pieces and just chop it up into 4 pieces and then write your variables on there. Because again, it doesn't matter that they're to scale, it matters that you're picturing how they all relate to each other. So either way, it'd be fine. We're not interested in the artwork, we're interested in the math behind it. Okay, so now we can more clearly see the relationship between the parts. Some of the problems I've recently seen you all work, this would have been a great way for you to do it. Chopping it up, drawing something visually, and then kind of chopping it up. We worked a problem recently that had a lot of fractions in the word problem. But I think if some of you had drawn it out and drawn a visual before you ever got to the fraction part, I think it would have helped you, and we'll practice some of those in class. So now we do need to write an equation, so we're going to continue on from there, but I just want to remind us that our next steps are we want to define the variable and write an equation. So what we were just doing was in order to write an equation. Okay. So now, first thing we got to do is define our variable. We sort of already did that here, so we're going to say x is the first. Let's be more accurate because I'm always getting on you guys about that. X is really the length. It's not the piece itself, it's the length of the first piece of tubing. So now we define our variable, we want to write our equation. So we have to go back up and look at remember that the crucial thing is that the whole tubing is 50 feet. So really, that's where I like this drawing here a little better, because it helps us remember that they all total up to 50. For me, when we draw it like this down here, it can help me lose track of the fact that the total is 50 feet. So here I've got my 50-foot thing, I draw it out, I know it's 50 feet, maybe I even label it as 50 feet. So I remember that, and then I start doing my work. So now when we know that, we know they all total up to 50 feet, then I just do my x plus, so that's that piece, this piece here, plus my x plus 5, plus x plus 10, that's the third piece, plus 2x, which was the fourth piece, and all together they make up that whole 50-foot piece. So we took our drawing up here, we did some labeling, reading word problem, labeling the drawing, and then we wrote an equation. Now, again, we're not going to solve this equation. You all know how to do this. You're going to combine like terms, solve an equation like you would any other equation. So the hard part about word problems is not solving the equation. You all are pretty good at that. What people struggle with is writing an equation from the word problem to begin with. So that's what we're trying to emphasize right now. So we defined our variable, wrote an equation, going to let you handle the rest there.